Welcome back. So we are back on Algebra 2 Semester A, Unit 1, Functions Tutorial Part 2. We're starting picking up where we left off, slide 18. So we're going to go ahead and discuss about the domain and range. So think about the domain and range as a sense of like, where does our function spread out to? So when we're talking about the domain, we're talking about where does it spread out horizontally, and when we're talking about the range, it's where does it spread out vertically. So let's go ahead and take a look at this example here. So they it's actually very familiar. Actually, is it almost the same as slide 17? Let me double check quickly. So it is very similar. It's actually the exact same thing as the question that you dealt with in slide 17. So have you already figured that if when we read our graphs, we read them from left to right. So with that said, as we read it, right, this line right here, now I know in the picture it looks like they're actually overlapping and they're right and it's right next to each other. If anything, you can say like that line is touching y is equal to 4, which is that red dotted line. It actually, if we zoom in really, really close, it's not. It's so tiny and yet so close, but it's never actually going to touch. And we call that red dotted line our asymptote. So our exponential functions do have a horizontal asymptote, meaning it's going to get closer and closer and it's going to keep on going forever, but it's never going to actually touch. So we do know that this is an increasing function, which is what they're stating right here. And then again, we already talked about that asymptote. So the question is, understanding the asymptotes help us determine two more very important features of the functions of domain and range. So let's take a look at quick note of what they're going to look at, notation. So you're going to see notation like this, not so much. You're going to see it mainly in interval notation or with inequalities, but we'll go over that in the next couple of slides. But again, so let's just talk about the domain and range. So the domain, if you also think about it in math, we like it in alphabetical order. When we plot coordinates, we always use our we look at our x-axis first, and then we determine the number for along the y-axis. So domain is going to be strictly along the x-axis. So from where to where does this graph spread out on the x-axis? So if you don't, I'm going to go ahead and expand the lines a little bit here, and might be a little crooked, but this is forever going this way, right? Because it's going to try to get closer and closer to 4, but it's going all the way towards the left. Now, if we take a look at this one here, towards the right, it's actually going up like this. So even though it's spreading up really, really fast, it's exponentials tend to go at a faster rate. They start out pretty slow and then they just skyrocket. So the thing is, we're seeing it stand kind of like almost not saying straight, but it's getting pretty steep. The thing is, as we look at it towards the right, it's gonna have like a little tilt where it is moving off forever to the right hand side. So for in this case here for the domain, it forever goes to the left and forever goes to the right. And technically, when we think of that forever, what do we represent that? If we're talking about the left, we're going to say negative infinity and this side infinity. So interval notation would be for the domain. So I would put capital D here like this and say it spreads from negative infinity to infinity. There is another way you can notate this, and I'll write it right here. You can say that it's all real numbers. So it's that R with an extra line there to represent all real numbers. Now, another thing to consider is the range. So the range, do you see, we talked about where it spreads out horizontally. Range is how it spreads out vertically. So for vertical here, I'll do it in red. It's that asymptote is actually helping us out here. The lowest point, do you see? It's trying to get to the red part, and then it's forever kind of goes up. It extends up. So keep in mind that red line is not actually part of the exponential function. It's just, I'm just kind of showing you that it's going to forever go to the top. So again, that word forever, right? it's infinity because it's in the positive direction. Now, the lowest point that it reaches is this 4. And the thing is, it now I'm saying it incorrectly because I'm saying it's reaching for, it's going to approach 4. That's the correct word. Approach 4, but never actually touch 4. So when we talk about the range, we would use the capital R, and we would say that this goes from, you want to start with the smallest number to the largest number. So here the lowest point is 4. Keep in mind I put parentheses because it means that it's getting closer and closer to 4, but it's never going to be 4. If it's allowed to touch 4, it would be a bracket, meaning it can be that number. But remember that whole idea about the number lines and graphing on the number lines with inequalities, open circle versus closed circle. Closed circle would be a bracket, open circle would be a parentheses. So right here we have 4, and it goes all the way to infinity. So this is the domain range for this specific function. Again, exponentials will always have an asymptote, and we'll go ahead and move on to slide 19. So again, it's an overview of the domain and range. Here, they actually brought out the different notations, kind of like if we clicked on that blue link listed on slide 18, there was a different set of notations, and we kind of already went over it. But this one is for a different function. So for a linear function, it says, for functions f of any real number may be used as an input, and any real number is a possible output. So the domain here, a linear line, I like to extend it so we just get a bigger picture of it. Let's do it like this. It's going out that way, and then it's going out that way. So I know it's like big, why I'm making it larger, just to get the idea. So you can see it's kind of stretching all the way to the left and all the way to the right. So it's going out to negative infinity, and it's also going out to positive infinity. That's how we determine our domain. So I am more used to writing it in interval notation. Occasionally you're gonna see this one, but with momentum, they like interval notation or sometimes inequalities. Again, another way you can also say it is all, you can actually write it out, all real numbers. I'm just gonna abbreviate numbers there. Or you can use this R here. Got it, it's the same R right here. For x of all real numbers, it goes from negative infinity to positive infinity. How about the range? Range, remember, talks about the vertical point. It's going to forever go up and forever go down. So then again, we also do negative infinity to positive infinity. Keep in mind, look at the notation. Here, they used f of x. Remember, f of x is the same thing as a y. Here, they use the y. Again, f of x and y can be kind of interchanged. The reason why we use f of x is just to let us know that it is an actual function. Let's take a look at the quadratic here. So the quadratic here, it's a little bit different in terms of range, domain and range. Its domain and range is going to vary depending on the function you have. It's it's best when we have a picture, because like I said, pictures are a lot more nicer. I like pictures. So for domain, this parabola or this U shape, right, is kind of, like I said, it's like the idea, but the exponential. Oops, kind of curved off a little too much there. But it's slowly curving and stretching out. Now, it's like we see this part of the picture, but if we were to see it little by little, you're going to see that it's starting to kind of spread apart. So for the domain, it does go all the way towards the left, all the way towards the right. So that would be from negative infinity to infinity. Now, what about that's the domain. What about the range? The range is, again, the vertical stretch part, right? How far does it spread out in the vertical sense? So here, I do have a low point, which is at -1, and then it goes all the way up. So if it's forever going up, again, that keyword forever, we have infinity. And it's in the positive direction, so positive infinity. So that is where there's two ways you can say it, where the y value, right, is greater than or equal to -1. And here, I'll write it in interval notation as well, because it can be at -1. It's sitting right there. So then you can also say, again, the lowest point is -1. You see my bracket there? And it goes to infinity. So again, when you're also writing in infinity, it's always going to be attached with a parenthesis sign because, again, infinity goes on forever. We don't know how um, infinity can go really, really fast, or it just has different rates. But infinity, it's not known where it stops. So we use a parentheses for that one. Uh, Again, there are several different ways you can write it. Instead of me writing it as y, I can write it, the function is g, so we can write g of x. So my y right here, I'll just change it, oops, to look like a g, and just write g of x is greater than -1. Again, that just represents the same thing as I have y value there. Let's take a look at this exponential here. So for function h, any real number may be used as an input. However, only possible outputs are the numbers that are greater than but not equal to 4. So that the domain again here is going to be forever to the left, forever to the right. So all real numbers, or -infinity to positive infinity. The range is different. Here it's getting closer and closer to 4. Now it looks like it's touching 4. But like I said, if we were to zoom in really, really close, you're going to see that there's a tiny little space in between. So the lowest point that it's trying to get to is 4. Now remember, it cannot touch 4, so we're going to use a parentheses. And we know that it's going to spread going up forever, so then that is infinity. Again, this is for the range. The domain, actually the domain for all three examples that we saw, they're all from -infinity to infinity, or all real numbers. Moving on to slide 20. When it loads. There we go. So it says, now let's look at the domain and range for our functions from the beginning of the lesson. We need to consider only the values that are reasonable within the context. So for these functions, we look at the positive values. So another thing to keep in mind, so we're going to look at the right again, which we saw in our warm-up, or we were dealing with in our warm-up in the beginning. So part 1 of this, of the functions tutorial. With these, considering the domain, right? Because the domain is probably, the domain and range is going to be restricted in terms of a word problem. I know we saw that a lot in, did we see it in the previous tutorial? I think we did see it in the previous tutorial when we were solving. I think it was like the last question or the last 2 problems we probably went over. The when we are solving for the answers, because if it was just a regular equation, we would have all those answers work there. But we have to consider, if we're dealing with a word problem, and consider the context of the problem. So I think one of them was where the example that we saw before was about measurements of a fence, and a portion of the answers that we had were in the negative part, and then we had like all the way, I think it was like -20 to +15, I think, roughly. The negative portion of it we couldn't consider because, like I said, if I go to Home Depot and I say, can you cut me -20 feet of this board? That doesn't make sense. There is no such thing as cutting -20 feet long of a board. So we would have to ignore, or kind of like put aside the negative portion and go from 0 to 15, because that is a more reasonable answer. So that's what we're going to go ahead and consider in the next couple of slides here by looking at these problems. So it says right here, now let's take a look at the domain and range of our function from the beginning of this lesson. We need to consider only the values that are reasonable within the context. So these functions will look for the positive values. So also think about it in terms of time. Time for a ride, right? When you got on the ride, when you're sitting on there, that's start the and they turn it on, that's starting from 0 seconds to going up. It doesn't, this function can actually continue. I can extend the line over here. It can kind of continue on here, but if you think about it, on this x-axis, we're talking about negative time. And there's no such thing as negative time. That's why we wouldn't even consider that side. We won't even pass 0 because there's no such thing as -3 seconds. So we start at 0. And now let's go ahead and continue. It says, for the linear relationship describing the trip up the tower, the time can be valued between 0 to 17.5 seconds. The height can be at any value from 0 to 350. Both the domain and range contain the infinite number of values within the boundary, so the continuous function, and is graphed as a solid line. So remember, we are limited because the ride is the tallest point of the ride is 350 feet. I think it was 350 feet. Yeah. And it looks like it only takes 17.5 seconds to get up there. So it makes sense that we shouldn't have any more, once you reach the top, there's nothing more up above. So we need to make sure we consider that we have a stopping point, right? Because it says trip up the ride. So you start at 0 seconds and you work all your way up to you're at the very top, which is in 17.5 seconds. Where are you going to be at 18 seconds? You're still going to be at the up at the top because again, you already reached that maximum height of the tower. Now let's talk about the free fall, right? The free fall is going to have the same drop every single time. So again, these functions can continue, right? This is a parabola. It's probably going to look something like this. Rough sketch. I know it's a little curved off, but the thing is, this side doesn't exist because this represents negative time. And then also, if you think about it in heights, it doesn't make sense that the ride goes below ground, right? This at the zero line is pretty much it's when you've already landed back to the original position that you're at, which is at the 0 feet. So it doesn't make sense that we would be in this negative area down here. So that means it goes below ground. We don't need that. There's no rides like that. So we are restricted here. It looks like the free fall when they drop you. So once you reach to the top at 288 feet, which makes sense, right? Because the tower itself is 350 feet. You're not going all the way to the top, right? There's always a sign and you make it reach up close up to the sign. And then that's when you do the free fall. Here, they also write out the domain and range in a different, in different, um, oh my goodness, I'm losing my train of thought. They wrote it down for you for the domain and range in different things. So here, actually, we have it in interval notation. I didn't even talk about this last one. This last one, they actually wrote it in kind of in inequalities. It represents the same idea. But again, it's all pertained to their specific graph listed above. So here, the highest point that it's reaching is at 288 feet. The lowest point is 0 feet. For the domain, which is about the time, right? It's going to be from 0 to 3 rad over 2, 3 rad 2, which is similar to 4.224 seconds. So let's move on to the next one, which is the riders. So this one, oh, hold on. Is this an exponential relationship also continuous? Can we conclude any values of the boundaries? Okay, so we're talking about the age group, which is these are discrete points. There is no we're not gonna connect dots like that and make it look like an exponential, even though we kind of determined before it is an exponential function. The thing is, remember these each point represents a age group, right? You're not gonna the reason why we don't put that line because it's a discrete function, meaning we're using only whole numbers. You can't have a well, it's true, right? You can say like, oh, I am 16.5 years, meaning you're 16 and a half. And instead of saying 16 and a half, just say you're 16, right? So the ages we're using, that's the idea about the discrete numbers are just whole numbers. If we're talking about like you want to say, oh, I am 18.5 years old. Doesn't make sense, just say 18, right? So we use those whole numbers. That's why these are not connected online, because if they are connected online, we're actually including those 0.3 or 14.7. We're using just strictly whole numbers for this one. So the domain here is actually listed. So it would be 0, 1, 2, 3, and 4. And remember, each of those represents the age groups, right? For 0, I think it was like 12. No, was it like 12 to 19? and then like it increases per interval of age group. And then the range is again how many writers are specifically for there. But like because we don't write it out as how we saw the two domain and ranges for the last two, is because these numbers are not connected. So we just actually list them out there for us. Moving on to slide 21. So let's talk about the key features. So we've determined that the domain and range of these three real world functions and whether they are continuous or discrete. So these two are considered continuous functions because they're connected, discrete because they're not. What about their other key features? Take some time to identify the key features. So remember, key features. We have, you can tell me when are they positive, when are they negative, or like when is the function positive, when is it negative? Do we have any x-intercepts? Do we have any y-intercepts? Is the function increasing or decreasing? And so on. So think, yeah. So we click on each graph. They're telling us it is a linear function. It's increasing and positive over the entire domain. Remember, it is limited. They do have a slope. They did list the slope for us. So when we have linear functions, we will be just stating out the slope. It does say that they have an x and y intercept. So if it's actually at the point of 0, 0, it's listed technically as both x intercept and y intercept. And that's the only intercept we have. If we look at the next one, which is a quadratic function, right? And you saw me draw the parabolic, the U shape, upside down U. It says that the vertex, so quadratics have a vertex of 0, which is at 0, 2, 88. It does have an x-intercept. And not only is at 0, 288 the vertex, but it's also our y-intercept as well. So they have that all listed for you. And then you can go ahead and take a moment to look at the exponential. Let's move on to slide 22. So the parent functions. What are parent functions? When you deal with equations, like say we deal with this equation, y equals 2x plus 3. This originates from the parent function, or y equals x. So parent functions is like the foundation of each function here that we're going to see. But do you see the difference? It's like, oh, the new changes here is that the x got multiplied by 2 and then they added this 3. So this, if we were to take it away, right, it looks exactly like the parent function. So parent functions, there are more, it's just more than y than x. It is also y equals x squared. Y equals, what's another one? X cubed. And I can kind of continue on from there. But these are considered our parent functions, and we're going to look at the changes from what did they add, because that 2 represents something to us. That 3 also represents something to us as well. And we're going to go ahead and talk about that. So, so for this one right here, we're talking about the quadratic of y and f of x equals x squared. Here's our exponential, and here is our linear. It looks a little bit different compared to what I wrote, but it's very similar to this. F of x equals x squared is the same thing as y equals x squared. For an exponential, it's y equals 2 to the power of x. Remember, those f of x's can be swapped out for a y. So these are the 3 different functions in this lesson. We're going to see, we've been seeing linear, quadratic, and exponential. Functions that belong to the same function family have similar features and characteristics. So what makes it different when I write out a different equation but base it off of the parent function? Again, this is the original. I can make up another linear line that looks like this. A little bit more steeper, a little bit more shifted or vertically shifted, or horizontally shifted. There are multiple ways to say it for linear, but that we're going to go into that. So again, these are the parent functions. We're going to go look at how we change those around. So let's take a look at this one right here. For linear transformations, what's the difference, or what the change that we see? So again, y equals x is the original. This second one became y equals negative x. The change from the original to this one is that negative right there. That negative, do you see how if you think about it, we're reading it, it's like your car is traveling uphill. Adding that negative there, it actually made it go downhill. So the negative actually does a reflection over the x-axis. Now, that only happens when the negative is outside. There is a reflection over the y-axis, but that's when the negative is inside, which I will explain a little bit more as we continue on. So let's focus on this new one here. Oops. What's the difference between y equals x and y equals that purple line, y equals 3x? The change from here is y equals x, and now we have a 3 there, is that it got vertically stretched. Now, the proper term is vertically stretched, which I think, they talked about it as dilation, which means that it's vertically stretched or compressed. When we do vertically stretch and compress, I can't exit out of this, can I? Oops, there we go. All right, vertically stretched by a factor of 3. So if you think about it, it's kind of like if I want to go hiking, right? Well, I rather hike on this one because y equals 3x, that line, that purple line, it's a lot more steeper because it got multiplied by that 3. What about the orange line? By 1/3. This is an example of vertically compressed. How would I know the difference between a vertical stretch and a vertical compression? It's the actual value there. So the value is between, here it's between 0 and 1. So we'll say that we'll call it A. Oops, that doesn't even look like an A. My mistake. If it's between 0 and 1, a decimal or a fraction, it is going to be vertically compressed. So that's an example of compression or compressed. When it's stretched, its A is going to be bigger than 1. That's when it is considered a stretch. Stretch. So those are when you're multiplying into it. And keep in mind, we're breaking them part by part, meaning there's a reflection, there is vertically stretch or compress. And then we have also the horizontal and vertical shifting, which here they're going to go with vertical translation. Okay, so this plus 4, my y equals x line was right here. But because we added that plus 4, it's like we picked up that line and we brought it up 4 units. And if you actually count it, so if you pick a point from my y equals x line here, say I pick a point here, because I picked it up 4, it should have the same distance. So 1, 2, 3, 4. It's on that purple line. If you choose one back here, 1, 2, 3, 4. So remember, and so I made a note that it's like when I say outside, again, I'll explain that, but I'll explain the difference between outside, when I say outside and inside, to kind of help us indicate whether it's a vertical translation or a horizontal, or a vertical transformation or a horizontal transformation. Now, what happens if I want to bring it down? What sign would I use? Here we used a plus 4 to bring it up. We do the opposite to bring it down. We use a minus 4. So that minus 4 brings it down 4 units. Again, it's like picking up the black line and then bringing it down 4 units. So now let's go ahead and take a look at slide 25, which looks like it's a question. Okay, so it says use your understanding of transformations and key features to write a slope-intercept equation of this linear function. So for this one, it is based off of the transformations and they're asking you to do it, but you can just go ahead and stick to, this is from the slope-intercept form. So the only values you need to enter is M, the slope, and your B is the y-intercept. I like to start out with B first. Oops. So if you look at your graph up above, what number is it touching on the y-axis? So that blue line is touching Take a look. Isn't that touching? What number would that considered? So you're going to type that number in there for me right here and replace B. And now to find the slope. So I already placed my point on the line there. I can choose another point that lines up perfectly, which is like right here, and find the slope. Now, from the graph, I like to count. It's always rise over run. Now, if you think about rise, when you're rising, right, you're thinking about the vertical direction. So from starting this point here, I'm going to say this is A to B. For me to get to A, I'm not going up, I'm going down 1, 2. So to represent going down 2, I'm going to put -2 over what's the run? Run to the right, that's 1. And we simplify that, -2 over 1 is -2. So that is your M right there. So go ahead and make sure you enter those values for M and B. Moving on to slide 26. Looks like it's another question. Okay. So this one more, it's best if you take your notes and actually kind of play around with these the sliding tools. So there are actually two graphs here. It is one is in black and one is in kind of like this yellow gold color. And they want you to mess with it. I'm going to rewrite this for you. So the format is the original. I know it's written really weird, but this is y equals x squared. So we're actually using the parabola. Now, what is this one written out as? It's just the way they formatted to type it in, it just came out weird. So this is a parentheses x minus h parentheses squared plus k. So what happens if you change this a? So what I'm going to do is I'm going to change this interval to 0 first and start with just 0, 1. I want a to be positive. Now, if it's from 0 to 1, look what happens when I get it closer to 10. What happens to my gold line as I'm moving it, getting closer and closer? What do you see? You see how it's kind of stretching up a little bit? It's actually becoming more narrow. What happens if I decide to change this value from 0, instead of 0 to 10, I'm going to just say from 0 to 1. What happens if I move it closer to 0? Look how it's expanding. The A, when A is positive, this is the idea about the vertical stretch, vertical compression. So this is actually an example of the function. So this is normal, right? Y is equal to x squared. If I bring in a decimal or a fraction less than 1, kind of like what I wrote, my note that I wrote before in that other side, is when it's vertically compressed or stretched, this is compression. When the smaller it gets, it's very weird. I know it's actually, a lot of people tend to say, oh, it's getting we would say wider. And people have that misconception where, oh, it looks like it's getting bigger. It's actually, this is an example of compression. The smaller it gets, the wider it gets, it's being more compressed. Now, if I back this to 10 and bring this back to 1, so greater than 1, when this is an example, when anything is greater than 1, it is being vertically stretched, making it more narrow. And the thing is, with the idea, again, people think it's making it smaller, but it's actually it's stretching it longer. Kind of, in a way, I think about it as like jump ropes, where if I pull the jump ropes together, I'm bringing it more, I'm extending it more towards me. And if I spread them apart, it's actually making it a lot more smaller. That kind of makes sense. I hope it does. If it doesn't, I'm sorry. So that's through the A value. This messes with our vertical compression and vertical stretch. So remember my A, that's why I wrote A. If A is greater than 1, then that is a vertical. Let's just add that. I'm going to put V for vertical, and then that is stretch. And when A is between 0 and 1, it is a vertical compression. vertical compressed. Sorry. Now, what happens, I messed with it so I didn't get negative here, but the same applies when A is negative. But this is kind of like the absolute value of A. Let's put it that way. Because when A is negative, so when you have a negative A, it is a reflection over the x-axis. And I'm going to demonstrate that for you right now. So let me change these values here to -1, or let's just say -10. And let's just put this as -1. So you see, it is a mirrored image, but reflected over this line right here, the x-axis. So what happens if I move this closer to, what if I make this number larger? Do you see? It's getting more narrow. It's very similar to what we had it up in the at the top, but that's when A is positive. That's why, again, I included the absolute value signs, because then we can know, well, we know it's reflected over the x-axis, but stretched vertically by a factor of whatever the value of A is. Now, what happens if I make this, let's put 0 here and change this to -1. So it's still facing down, right? It's the same size as the original one because it's at -1. So just the negative is the only change there, which is, again, reflection over the x-axis. What happens if I make this smaller? Do you see how it's getting wider? So you are going to be able to make statements like, oh, it is reflected over the x-axis and vertically stretched or compressed by a value of whatever your A is. Now that we talked about changing the size, let's talk about the horizontal and vertical shifting. So I'm going to actually bring, oops, I kind of messed with that already. Let me bring this back to, oops, highlight 0. Close. Okay, let me put 10 back here. And let's change this to 0. Okay, so now we're back at 0, 10. I'm just going to keep it the way it is. We're not going to mess with A. We're going to just make sure it's just 1. And let me put this, bring back this to 0. So let's talk about what the H does. So remember what I said about the new changes. A is new to this x squared. This H is new. This K is new. But they all do their own part to this graph. So what happens if I move H to a positive number? Do you see H is moving towards the right? But that's if it has a minus in front of it. So if I keep in mind, this is like minus 7.4. If you have a minus whatever number, it's going to move to the right. What happens if I move it to the left? Say I want to move it at -10. The center used to be at 0. Now it's at -10. Keep in mind, I'm writing it out like this. -10, right? Because that's H. That just comes out to +10. So when that H value, whatever sign you have, if it's a plus sign, you want to think of, oh, plus signs to the right, it's opposites to the left. Whatever that number is, how many times you go to the left. If it is minus a number, it is going to move towards the right. Now, if this is left and right, this changes the size, this moves it left and right. K, what's the only other option there we have left? Then it moves it up or down. So let me bring this back to 0. Oh, wait. This is supposed to be 1. Messing with these all. And let's mess with K now. So K, if I want to move it with that plus sign, you see it's going up if I'm moving it towards the right, and minus K, so it'd be like -9 or -9.8. It's bringing it down. So it's the same shape. It's just you drag it down. H and K is pretty much your vertical. H is your horizontal shift. K is your vertical shift. Which I will make a note to make sure that we write all these rules down. Let's take a look at slide 27, where we look at the exponential value. So it's very, again, these rules, they're not always going to be the same, but we're going to go ahead and take a look at it. I just don't like that the way it is written out. So this one, it's not 2x, it's y equals 2 to the power of x. And this one is y equals a b to the x minus h power, and then plus k. So keep in mind, b is your value, is your base, that 2. A is again that vertical, it can be vertically stretched or compressed. H is going to be the horizontal shift of left to the right, and K is going to move it up and down. Let's talk about H and K first. I think I rather see H and K before we mess with the other ones, but let's move H. Now remember, if it's X minus H, let me put that in parentheses as well. So remember, if I move this, it's going to be minus 3. Do you see? It's moving it off to the right. And I'm going to move it to the left. It's moving it back that way. So it still stays in the same shape. It's just H just moves it left or to the right. Let's take a look at K. K moves it, remember, plus whatever number, minus is going to go up, minus whatever number is going to go down. So that H and K is pretty much standard for all the functions, especially if they write it for you out like this. Now, what happens to A? A, remember, as A gets bigger than 1, it's, do you see how it's actually, think about it in terms of a roller coaster. Do you see this, the gold one, which is the one that I changed, it actually got steeper, and meaning a vertical stretch. This one is the original, so kind of think of like Superman at Six Flags, right? It kind of has this like little tilt to go all the way back up, and then you get dropped down. A, as it gets larger, it's going to get steeper or vertically stretched. What happens if I make A smaller between 0 and 1? So let's bring this to 0, and let's bring this to 1. And I make this smaller. Do you see? It's actually, remember that idea that about how it gets more narrow, it's a stretch. If it gets wider, it's going to be compressed. And let's go ahead and include our negative here. So let's bring out negative 10. And let's bring this to negative 1. So again, that negative is going to make it reflect over the x-axis. So do you see these rules are the same for every function? It's just you have to break them into properly break them down into pieces, especially when they ask you to break it down. So negative will make it reflect. Remember, if I keep this between negative 1, the larger it gets, the more narrow, or in a sense, it's getting more steeper because it's being stretched. Now, what happens if it changes to 0 and changes to negative 1? And I make this smaller. It's being vertically compressed after it's been reflected. So let's go ahead and discuss this more on slide 28. So for both the quadratic and exponential function types, changing the equations of the parent functions transforms the graphs to the functions similarly. So I think this one might actually provide all the rules. Give me a second. Yes, it does. So I know it is super important to write out notes. Here, they didn't actually discuss the reflection over the y-axis, which is completely fine. Let me take a moment to, yeah. So here it's the statement, translate k units up. So if you take the function f of x and you add a number to it, so like think of f of x, you can set it equal to x squared, x, or like 2 of x. When you add a number to it, so that can look like x plus 3. Because it's plus 3 at the end, that means that it's 3 units up. What happens if it's going down? Well, let's bring x squared here. X squared minus 3. That is bringing it down 3 units. This is what, now these numbers are changes on the outside. This is where I'm going to bring it up. On the inside. Actually, yeah, let me take a moment to rewrite my notes here. Okay, so I took a quick moment to go ahead and write it out like this. I know it looks pretty much, the idea is what I wrote on the right-hand side is, again, very similar to what you have on the chart. I just I don't know, for some reason I like the description on the right hand side. That's just me. But keep in mind, these are f of x represents the parent function. So that could be x squared, it could be x. And what I did a little bit different is that I wrote h in here for the horizontal translations. I know here they're referencing it as k. And here they say like k when where k is greater than 0 and k is greater than 0, k units to the left. See, I just reorganized it a little bit different. So when you have f of x plus k, and I'll give you like quick little examples over here on the left-hand side in blue. So let me start from the very top. So again, these are f of x is a parent function, a times f of x. So when absolute value of a, so meaning just the positive value of a, say our f of x is going to be, let's just say x squared. It's x squared. It's a parabola a of x squared. So when a is greater than 1, so when it's 3x squared, right? Again, the original parent function is x, or like I said, it could be x and then it'll just be written as 3x. It means that the parent function got vertically stretched by a factor of 3. That new change there. I know I'm going to try to line it up as best we can. What happens if a is between, the absolute value of a is between 0 and 1? So like, let's just say 1/2 x squared, and this is 1/2 x. Then you can say that it was vertically compressed. So the x squared or x was vertically compressed by a factor of 1/2. Now let's talk about the vertical translations, which is moving up and down. So again, do you see I'm kind of doing both parent functions here for the quadratic and the linear. F of x plus k. So I can have x squared plus 2. X plus 2 can be written, and that means that it's k units up or 2 units up. What if I have x squared minus 3, x minus 3? Then that means that the parent function got shifted 3 units down. So this is the difference between that whole idea about the outside versus inside. These numbers are kind of lingering outside of the original parent function. That means it's a vertical translation plus when we look at any transformation vertically, the concept of it is that if it's straightforward, so plus sign it's going to go up and minus will go down. Now horizontal transformations are the opposite way to think of. So again, here is an example of a horizontal translation of to the right. So it'd be x minus, let's just say 4. I know I'm going in order, but parentheses squared. You're still going to get that x squared, but that minus 4 means that that parabola moved 4 units to the right. Now, for linear, it's actually written a little bit different. It could actually mean, it could be x minus 4, or what they can write is that it's f of x minus 4. I know it's overlapping, so I'm sorry. F of x minus 4, or just like x minus 4 can be could be rewritten as x minus 4, means that it is 4 units to the right. Now this one looks very similar to what we just saw up here, but it's the inside the notation that makes the difference here. So then if you can see, this is moving it to the right. Now to the left, it's going to be x plus 5 parentheses squared. So this is an example again for the parabola. Now, if I have a linear function that is which is equal to f of x, right? I can say that the linear function became f of x plus 5. This is again a horizontal translation of 5 units to the left. If it's f of x plus 5, so the 5 is lingering outside of the function name, this is 5 units up. That's like the main difference. Do you see what I mean by inside versus outside? The number is hanging outside. The number inside here is hanging inside. Inside will always represent the horizontal transformation. Now, because it has a plus sign, it's going to move it to the right, to the left, sorry. And then this one right here, because it's outside of the function f of x or just x, that is going to be 5 units up. So please be very careful with that. I think it's just the linear in general that makes it a little bit more a little bit more confusing, but I want you to see a clear example with the aspects of a quadratic. Now, how do we, now if I have negative x squared or negative x, it is just a reflection over the x-axis. I am not bringing up the reflection over the y-axis because they didn't mention it. So they only want you to cover this. So you have two options. Either you can look at mine and kind of compared to the examples that you see there in blue, or you can just take a screenshot of the actual chart. So keep in mind that chart is linked on slide 28, where you click under transformations. They do provide another video, which I won't play, but you can go ahead and click on it. I think it's through Khan Academy. They go a little bit more in depth into transforming parabolas. Keep in mind, that's what I brought up. That's why I wanted to bring it up with this in blue, because you're not only going to just get one single transformation. You might have where I say like shifted to the left and then shifted up. So keep that in mind. This is how it's notated for parabolas. It looks like that Khan Academy video that is linked right there, also on slide 28, is going to give you more in-depth explanations with those transformations. But let's go ahead and move on to slide 29, and let's go ahead and answer this question here. So we're going to determine, it says function g is a transformation of the parent quadratic function f. Which statements are true about this function? So what happens if I write it out in this type of notation in black? So what I'm going to do is clean this up as much as I can. And we're going to rewrite this, or we're going to take a look at it. So remember, this originated y equal, or let's say f, because that's what they're calling it, f of x is equal to, I'll do this in blue to have some variance in here. So f of x is a parent function, which is just x squared. So do you see there's your x right there, and there it's going to be squared. But what are these new changes? So let's analyze first the first thing right there, that minus. Remember the minus on the outside of f of x? So I'm going to actually make the new changes to this based off of f of x, which is x squared. So it's going to be negative f of, it looks like they put an x minus 4 in here. So x minus 4, and then they put a plus 6 at the end. So let's take a look at this. So that negative, we see that there's a negative in front of the whole f of x. It means it's a reflection over the x-axis. So we have something with this. X minus 4 is on the inside. That's the same thing as x minus h. So we know it's 4 units to the right. This plus 6 is lingering on the outside. We know that it's going to be shifted 6 units up. So let's go ahead and read each statement to see which one is true. It says function g is reflected, g, so this new one, right? That new change, this is g. This is equal to g. Is f is reflected a function f across the x-axis. That's this one that we checked off here first. So this one's true. Function g is translated the vertex from 0, 0 to negative 4, 6. Well, okay, think about it in terms of a graph. If our parabola normally starts at 0, 0, we know that it went 4 units to the right, so 1, 2, 3, 4, and 6 units up, so 1, 2, 3, 4, 5, 6. So the position here is 4, this is 6, so this is 4, 6. So our vertex, again, remember our graph looks like this. Now our graph looks like this. It's going down because, again, it's reflected over the x-axis, and then it shifted 4 units to the right, 6 units up. They're saying the new coordinate's negative 4, positive 6. So that's like 1, 2, 3, 4. Again, it's just to prove the statement. My red doesn't line up with my black dot over here. So this one doesn't work. Function g as x approaches negative infinity. So I'm going to leave this one here because this is the new function of g. It's not the exact one, but it's a rough estimate just to get an idea. So it says function g, so this black line here, or this black parabola, as x approaches negative infinity. So along the x-axis, we're going to negative infinity, means that we're looking towards the left. Negative infinity, g of x approaches negative infinity. Sorry, it took me a moment to read that because of overlapping. Is that true? So as I'm moving it to the right, is my graph going to negative infinity? Is it going down? So go ahead and select it if it's true. If it's not true, don't select it. Function g is always decreasing. Well, when we read graphs, if I follow this motion, is this decreasing? And then, but keep in mind the word always. Is it always decreasing? Are we sure about that? So then let's go ahead and take a look at that one, or move on to the next statement here. So is function g always negative? Remember, if it's always negative, it's always below the x-axis. Don't I have a top portion up here? So it's not always negative. A portion of it is negative, but that keyword you have to watch out for is the word always, meaning it's not going to be positive at all. It is. Function g is symmetrical at the point 4, 6. So what do they mean by symmetrical? They're talking about that vertex part or that vertex line. So at 4, 6, is it, again, mine is a rough estimate, so is it symmetrical there, or is that, isn't that technically, we already determined that this is our vertex point? And remember, our vertex point, our axis of symmetry will go through our vertex and cut our parabola in half. So is that statement true? Is it symmetrical? Is it, if I cut it, is it even on both sides? So go ahead and answer those. Select the statements that you think are true to that. And we have reached the end of this tutorial. Again, make sure anything that I write, you can go ahead and write as well, especially those key points about the translations, both like vertically, horizontal translations, the vertical stretch and compression. Those are super important. Keep in mind to determine if it is a function, you can, if you have a graph, vertical line test, or remember, if you look at the table under the X, they will not repeat. That's just like a little glimpse. Another thing we saw was domain and range and their key features, x-intercepts, y-intercepts. When is it increasing, decreasing? When are they positive, when are they negative? A lot of different, a big overview. And the main ones that we saw were linear, exponential, and quadratic. Now, keep in mind, though, the chart that I wrote on there on the side, I specifically wrote H in there because if they give it to you in an exponential setup, it's x minus h at the top as the power, and then k is brought down below. So the h, I always want to refer it as that horizontal shift, and k, that vertical shift of up and down when you're adding or subtracting those. And we reach the end.